when geologists want to study millions of years of Earth's history, we don't just look at outcrops of rocks at Earth's surface. We also look below them. We drill into continents, ice sheets, and even deep beneath the sea floor. But what exactly do we use these so-called cores that we drill for? Do we just count the layers and call it a day? And what do these cores tell us about Earth's past? Today, I'm going to walk through the various ways that we use geological cores to study Earth's past and predict its future, many of which I learned about on a recent Geological Society of America field trip to the International Ocean Discovery Program Gulf Coast Repository at Texas A&M. This facility stores cores from the Chicxulub crater, as we talked about in the previous couple videos, as well as other parts of the Gulf of Mexico, the Pacific Ocean, the Caribbean Sea, and the Southern Ocean. It houses over 100 kilometers of core and stores thin sections, smear slides, and residue collections from these cores, keeping them available for scientists to study. But before I go down a rabbit hole geeking out about this place, let's start with the basics. What exactly is a core? A core is a long cylinder of rock or sediment extracted from beneath Earth's surface. And just like the rocks exposed at Earth's surface, the horizontal layers in these cores represent geological deposition over millions of years, with the rocks at the deepest part of the core being the oldest and those closest to the surface being the youngest. So in a way, each core is part of Earth's geologic timeline. Some cores show subtle color or chemistry changes that record ancient climates. Others preserve fossils, volcanic ash, tsunami deposits, sea level changes, and in some cases, like those we've shown in recent videos, evidence of a massive asteroid impact. And scientists go through each and every centimeter of these cores, looking for clues that help us reconstruct Earth's ancient oceanic and atmospheric conditions. Some of the most common ways in which we analyze cores include looking at their isotopic compositions, thin sections, sedimentology and stratigraphy, microfossils, paleomagnetic signatures, volcanic ash, bulk and trace element geochemistry, and organic geochemistry, just to name a few. But let's back up a second. What do all these words mean, and what exactly do they tell us? Well, let's start with my personal favorite, isotopes. We measure radioactive isotopes which decay over time to date or determine the age of rock layers in the cores. And we measure stable isotopes which do not decay over time for a multitude of reasons, but one primary reason is paleoclimate. We can reconstruct aspects of Earth's ancient climate, including both oceanic and atmospheric conditions, using stable isotope signatures preserved in each layer of every core. For example, stable oxygen isotopes provide information about ancient ocean temperatures and by proxy ancient atmospheric temperatures, and thus periods of global warming, global cooling, in addition to global ice volume, glacial cycles, and sea level. Whereas stable carbon isotopes provide information about biological productivity levels, ocean anoxia, or periods of major oxygen decline in the oceans, and other major carbon cycle perturbations like massive greenhouse-driven global warming or cooling periods. Other stable isotope systems like nitrogen, sulfur, and boron can tell us even more. But we can dive even further into the details of Earth's past by analyzing trace elements like iron, manganese, uranium, molybdenum, vanadium, rare earth elements, and so many more within the cores. Ultimately, with the combined power of bulk chemical analysis using X-ray diffraction and fluorescence techniques, along with isotopic and trace element analysis using mass spectrometry, we can get a pretty clear picture of how Earth's climate was shifting over the course of time that it took for the layers in whatever core we're looking at to deposit. And we can even tell based on the residence time of different elements in the ocean which signatures indicate local climate changes versus global climate changes. Another cool type of analysis used on cores and many other rock samples in geology is thin section petrography. Thin sections are thin, polished slices of rocks that we can examine under a microscope. And if you've ever used a petrographic or geological microscope, you've probably noticed you have the option to view the thin section in either plane or cross-polarized light, which allows you to see a lot of beautiful colors of each mineral grain, and these are specific to the type of mineral and the structure and texture of the grain. Thus, thin section analysis can provide us information about the bulk mineralogy of whatever rock sample we're looking at, if it has mostly quartz, feldspar, olivine, calcite, etc., the textures in that rock, which can indicate the cooling rate of igneous rocks, as well as pressure and temperature of formation, the metamorphic grade of metamorphic rocks, the grain size and sorting, which is useful in determining the depositional environment of sedimentary rocks, diagenetic textures like cement, compaction, and dissolution, which can tell us about what happened to the rock physically and chemically after deposition and burial, and microfossils, which are typically only identifiable under thin section but can give us a lot of information about the biosphere at the time those layers were deposited. We can also look at grain textures and sediment structures without using a microscope, just by using good old sedimentology and stratigraphy. Sedimentology and stratigraphy are the bread and butter of core analysis. Our first impressions of a core are typically based on sedimentology and stratigraphy, through which we measure grain size and grain shape, sorting, color reflectance, magnetic properties, and sedimentary structures like laminations, stratification, bioturbation, which reveal depositional environments, wave energy of the environment in which it was deposited, whether it was river or deep sea deposition, whether the sea level was changing, increasing or decreasing, storm frequency of that region, turbidity or debris flows, climatic cycles like Milankovitch patterns, and so much more. So we analyze these cores at the atomic level with chemical analysis. We analyze them under a microscope, as well as just with our eyes. But hold on, what was this about magnetic properties? What do magnetic minerals in these cores tell us about Earth's past? Well, magnetic minerals in cores, like those rich in iron, retain the magnetic polarity of the Earth's magnetic field at the time they were deposited. Thus, studying enough of these magnetic minerals from different layers or time points along each core can provide information about past magnetic pole reversals, rates of seafloor spreading, since these magnetic minerals come from crust production at mid-ocean ridges, tectonic movement of plates or continents, paleolatitude or ancient latitude of continents, and so on. And I talk way more about how paleomagnetism helps us reconstruct the ancient positions of continents in this video, so I'll link that down below if you want to learn more. And even though this list of analyses barely even scratches the surface of the full list of analytical techniques scientists use on these cores, I hope this at least gets the point across that these cores can tell us a lot about Earth's past. And there's so much left to learn. Although we are still collecting more cores, many research remains to be done on the ones we already have. Here at the Gulf Coast Repository, researchers can request a sample and conduct their own analyses. And such independent analyses not only helps to corroborate previous analyses conducted by other labs, but also helps to collect new data on old samples when new analytical tools become available or more precise. The data from these cores, whether from the Chicxulub crater or the deep Atlantic, feed directly into paleoclimate models, which help us predict future climate changes on Earth. Okay, so now that I've told you about the really cool science done on these cores, I want to dive into some fun facts that I learned while researching this topic. First, what's the deepest we've ever drilled into Earth's crust? On land, the deepest we've drilled was around 12.3 kilometers or 7.6 miles. This was back in the 1980s in Russia, and the temperatures at the bottom of this hole reached up to 180 to 200 degrees Celsius. And unfortunately, due to the high heat and pressure at this depth, the technology at the time just didn't allow us to go any deeper. But even though this is technically the deepest hole ever drilled, it only got to about a third of the way through the continental crust. So a third of the way we needed to go to get to the mantle. Because Earth's continental crust is between 35 and 70 kilometers thick. So we've barely scratched the surface of continental crust. But you know what's a lot thinner than continental crust? Oceanic crust. So what's the deepest we've ever drilled into oceanic crust, and have we reached the mantle? Well, actually, in 2023, the International Ocean Discovery Program, the same one that runs the repository that I talked about in this video, drilled a borehole into the Atlantic that reached around 1,300 meters below the seafloor into mantle-type rocks like peridotite. This is huge because although we only reached the uppermost part of the mantle, these cores represent a major scientific milestone. Although that said, these super deep drilling projects are not the norm. Typically, cores are only drilled to depths of a few hundred meters, not kilometers. In any case, when it comes to studying Earth's deep past, we rely on the rock record, and this includes rocks below Earth's surface in addition to those exposed at the surface. So I hope you've enjoyed learning about some of the ways scientists analyze cores, what these cores tell us about our planet's history, and the importance of repositories like the Gulf Coast Repository here at A&M. And if you want to go on a GSA field trip for yourself, they take place all over the country and even internationally every year. The next set of field trips will be in March, April, and May during the 2026 GSA section meetings, and you can sign up now. Links are below. Bye!